Drywall is an important material in building construction and is used in walls and ceilings. Drywall is made of paper-lined gypsum and is extremely susceptible to moisture and damage. One instance where drywall can be damaged by moisture is when a sprinkler system goes off. These photos show drywall sitting in pools of water causing permanent damage. The goals of the study are to formulate theoretical models for the rate of diffusion of water through drywall and to conduct experiments to validate the theoretical models and provide recommendation for future studies. The assumptions for the theoretical model include unsteady one-dimensional molecular diffusion. There is no advection or chemical reaction. It is assumed that a similarity variable exists to relate the z and t variables. Two models were developed as part of this study. The simplified model assumes that the average mass velocity is 0, whereas the full model assumes that the drywall velocity is 0, while the water velocity is non-zero. The governing partial differential equations were then non-dimensionalized with a similarity variable eta. The resulting equation is a solvable ODE. The boundary conditions are applied to obtain particular solutions. The first BC is that at the origin z equals 0, the drywall is saturated to the value of rho A 0. The second BC is that at the far-field boundary, the mass concentration is 0. The simplified and full models were graphed to show the error that results by assuming the total mass average velocity is 0. As shown in the graphs, the shapes of the profiles are identical with a slight numerical error. Two experiments were conducted to validate the theoretical models. In the first experiment, a strip of drywall was submersed in water below the z equals 0 line, and the mass was measured at 10-minute intervals. From the measurements, the average mass concentration of water in the control volume was obtained. To compare this to the theoretical model, a linear average was performed on the distribution. As shown in the graph on the left, the experimental data has the same shape as the theoretical model but has a vertical numerical shift. This is likely due to an incorrect value of the diffusion coefficient attained on line. With a modified DAB, the data is a nearly perfect fit. The second experiment measured the distance that water visibly traveled through the drywall at 10-minute intervals. Similar to experiment 1, the drywall strip was submersed in water below the z equals 0 line. There was some ambiguity in this experiment because it was unknown what the visible water line represents in terms of percent saturation of drywall. It was found that the experimental results match the theoretical model when it is assumed that the water is visible at 30% saturation. The fact that the experimental data matches the exact shape of the theoretical model implies that the mathematics behind the model are accurate. Three conclusions have been formulated from this study. First, due to relative small error, it is recommended that the simplified model be used for future projects. Second, the shape of the experimental data matches the theoretical models perfectly with some numerical shifts. Therefore, the mathematical models are validated, but the originally assumed material properties were incorrect. Lastly, the recommended next step would be to create better models for the diffusion coefficient of water in drywall. Since drywall is a porous solid, it can be reasonably assumed that the diffusion coefficient would be a function of the drywall density.